Okay, then of course we have our next category, the aromatic amino acids, of which we have three. So if you take that same basic structure um, of the amino acids, right, and we put um, again, here's that carboxylate group, that amino group. We have a extend off the alpha carbon in the side chain position with a methylene group, and then add a benzyl ring. We of course have phenylalanine. If we then follow a similar theme, there's a methylene group. We now put an indole ring off the end of that methylene group. We have tryptophan, and if in off that methyl, that beta position, we now put a phenolic ring. We then have tyrosine. Okay, so phenylalanine actually may be the most hydrophobic of all the amino acids, even more aliphatic than most of the small. More hydrophobic than most of the small aliphatics. These guys, however, by comparison to those smaller side chains, even though they're quite hydrophobic in general, are much bulkier. So they're bigger. So there's a fundamental physical difference there. At the same time, if you look at these guys, think about some fundamental differences. That phenolic alcohol group has actually a physiologically reachable pK. Its pK is around 10.5, right? So that makes the hydrophobicity scale of these guys kind of go from right to left, the way I have these written here. Of the aromatic amino acids, tyrosine is going to be the least hydrophobic. Tryptophan is kind of intermediate. It's got a pretty good hydrogen bonding group available here, and that indole nitrogen. And then, of course, that benzene ring of phenylalanine is basically about as inert as you can get under most conditions, right? So if you think about my sort of that second category of things to consider about the amino acids in terms of reactivity, what do you think? Which one of those do you think is potentially reactive? Well, if you pick tyrosine, you got it right, right? That phenolic alcohol group, in addition to being an outstanding hydrogen bond donor and acceptor, and therefore having tyrosine be an excellent participant in acid-base chemistry, which we'll talk about in a few more lectures, that pK of around 10.5 can get in range where that phenolic group dissociates into a phenolate, and that phenolate, that O- group, can be an outstanding nucleophile. And tyrosine, under those circumstances, can participate in group transfer reactions, phosphorylations, and the like. Phenylalanine, by contrast, is again about as inert as you can possibly be. It's almost impossible to do chemistry on these things without doing radical chemistry. And that does happen, but we're not going to see any. Tryptophan also is not, for most of our purposes, we're not going to be thinking about tryptophan as a amino acid that participates directly in chemistry. There's not any really good ionizable groups there. You can get modifications of tryptophan, but again, not for any of the reactions we're going to be thinking about. Okay, there is an important additional property of these aromatic amino acids, of course. You guys may remember this, that as by virtue of all this conjugation that you see in these rings, the aromatic amino acids have, unlike any of the rest of the amino acids, outstanding absorption, right, in the UV part of the spectrum, right? So tryptophan, significantly more absorbing than tyrosine by about a factor of 5 or 6, which is about an order of magnitude more strongly absorbing than phenylalanine. The advantage to this is if you have a protein that has these aromatic amino acids in them, you can quite easily quantitate or determine how much protein you've got just by looking at this ultraviolet spectrum. And we'll come back to talking about something about how light interacts with matter in the context of basic absorption spectroscopy. Okay, but that's another important property of the aromatic amino acids. Okay, cyclic amino acids. We only have one. Of course, that's proline. So again, here again is that your alpha carbon. There's the carboxylate, the alpha carboxylate group. There's the alpha proton, and here's the alpha amino group. And if you imagine taking like a propyl 3-carbon chain, and instead of terminating it with a methyl group, you wrap it back around and bond it to create a secondary amine with the primary with the alpha amino group, you get this closed ring, pyrrolidine ring, that is, of course, proline. Now, proline has that, because of that closed ring structure and the way in which the alpha amino group and the carboxylate group are constrained near each other, has all kinds of important conformational consequences for protein structure. Proline is sort of intermediate in hydrophobicity. This sort of 3 carbons of this pyrrolidine ring are not, they're reasonably hydrophobic, but because of the polarity of the amino and carboxyl group, it's not unusual to find prolines sort of near the surface of a protein with these 3 carbons sort of tucked back down, but prolines can occur at the surface or all over a protein. They're sort of everywhere, right? In terms of reactivity, what do you think? Again, not a lot of potential for creating electron donating or withdrawing groups from these aliphatic carbons. You know, pK of those things is like 40 or something insane. No, got to be doing easy chemistry here. Proline does get modified. Hydroxyproline is not an uncommon post-translational modification of proline that you'll see. So chemistry gets done on it, but proline doesn't really participate as an active site of chemistry in the biochemistry we're going to be thinking about, right? Okay, sulfur-containing amino acids, we got 2. We of course have methionine, which is, again, there's the alpha carbon. We come down beta, delta, and then create a thioether bond. And then by sticking a methyl group on the other side of the sulfur, we create methionine. And if we go down just a methylene group and we stick on an SH, a thiol group, we create cysteine. Okay, now you're thinking about methionine and cysteine, in addition to having heteroatoms, right? They're sulfur containing, which has interesting implications. The cysteine, that thiol group, has a pK of, again, the isolated amino acids, it's right around 8. That pK can move around quite a bit. And because that is now right in the sweet spot for physiologic pH, that thiol can easily dissociate into a thiolate. And that thiolate, that S-, is an outstanding nucleophile. So cysteine, in addition, because of this equilibrium, to being an outstanding participant, a very common participant in lots of chemistry. You're going to see cysteine used over and over and over again for doing all kinds of basic biochemistry. That also tends to make cysteine, if it's deprotonated, quite a bit more polar on average than methionine. The basic hydrophobicity would scale this way from cysteine to methionine. That protonated thiol is actually pretty hydrophobic. And you don't really have to worry about, when you stick that in a polar environment, you don't have to worry, a non-polar environment, you don't have to worry so much about satisfying a hydrogen bond there, because cysteine is nowhere near as electronegative as oxygen or even a nitrogen. So hydrogen bonding is not really an issue for that sulfur group. And methionine is of course quite hydrophobic and is generally found buried. Okay. So in terms of thinking about chemistry, cysteine, oh boy, cysteine's a biggie. You do see methionine used in some important chemistries. SAM-based, S-adenosylmethionine, is one big example where the reactivity of that thioether is used to create this S-adenosylmethionine group, and that gets used quite a bit. But for most of the chemistry, we're not going to be talking about SAM-based reactions. You can pretty much think about methionine in our context for this course as not being especially reactive, but cysteine, oh boy. Okay, one of the things that cysteine can do that's super important is it can form a bond with itself. If you basically do removal of some electrons and a couple of protons, you can get cysteine to form a so-called disulfide bond. And that disulfide bond is a covalent, fairly strong covalent bond. And that can be used to pin different parts of a protein structure together. In addition to the primary covalent structure, you can link cysteine groups together to form these cross links that have all kinds of important implications for the structure and stability of a protein. All right. Okay. Hydroxyl containing amino acids, we got 2, right? We of course have serine. So if you go down to that beta position, and now you basically have what would be a methyl group. You pull off a proton, you put on a hydroxyl group. You now have, you have serine. You do the same basic thing again, but you pull off another proton and you put on a methyl group, hydroxyls in pretty much the same place, and you now have threonine. Okay, so if you think about those guys, you think about those little aliphatic alcohols, what do you think about their hydrophobicity? They're polar, right? They're quite polar. Those alcohol groups are outstanding hydrogen bond donating and accepting groups, right? They're very happy in solvent. They're very happy interacting in interactions with other hydrogen bonding groups in other biomolecules or in proteins. So they're actually quite polar. These amino acids are frequently, almost exclusively found on the surface of proteins, or if they're buried, the hydrogen bonding potential of those alcohol groups has to be satisfied in some other way, right? Because they're too polar to be in a hydrophobic environment energetically. What about reactivity? What do you think? You guys heard of any reactions where serine or threonine participate? Sure, I'm sure you have, right? Phosphorylations being a biggie, right? That alcohol group is actually can be coaxed into being a pretty good nucleophile for certain types of group transfer reactions, in addition to these guys participating in acid-base chemistry. And they can be used, and you will see this used. In fact, serine is a biggie for doing lots of important chemistries around splitting amides and ester bonds and things like that. That hydroxyl group is super important for those kinds of reactions. Okay. Acidic amino acids and their amides. Here we have 4 in this category. Of course, if we take the amino acid, basic amino acid, alpha amino acid structure, there's that methylene group again, and we put on a carboxylate, we have a aspartate. Extend the side chain by 1 methylene, again, a carboxylate, we have glutamate. These guys, of course, have pKs that are quite acidic, right? Down around 4 in general. If we take the same basic structure, right, we'll leave the carbonyl in place and replace the other oxygen of that carboxylate group with an amino group to form this amide bond. We have the amide derivative of aspartate, which is asparagine, and we can do the same thing with glutamate and make glutamine, right? There's the extra methylene, and there's the side chain amide. Okay, so you think about these amino acids, right? It sort of should be obvious. Are they, what do you think, on the hydrophobicity scale? They're polar, right? I mean, these guys, quite obviously, these charged carboxylate groups, great hydrogen bond donating and accepting groups, and that amide nitrogen, that carboxyl oxygen, great hydrogen bond acceptor. These are all quite polar. These guys are going to generally be found solvent exposed on the surface of proteins or in solvent, in contact with solvent in other places. What do you think about chemistry? Well, these guys, those carboxylate groups, are outstanding participants in all kinds of acid-base chemistry. You're going to see them all over the place, pulling and pushing protons around. Really, really common. They're not as awesome as nucleophiles. You do see these guys get used in some cases. In some group transfer reactions with that carboxylate oxygen will actually carry a group other than a proton. In terms of general chemistries, these asparagines, or the asparagine and glutamine, can also be used as acid-base chemistries. They don't do so much chemistry on their own, except with one exception, which is that asparagine and glutamine are absolutely essential to the whole branch of metabolism in which activated nitrogen is important. These are your 2 carriers, your primary carriers of activated nitrogen equivalents, right? We're barely going to get to touch on sort of nitrogen biochemistry, but these guys are central to it. They basically, you can putting on and taking off that nitrogen group by converting it into a carboxylate or back into an amide is super important. Okay. Basic amino acids. We're coming to the end of my scale. We have a few of these. If you take that alpha amino group, you extend 1, 2, 3, 4 methylene groups and stick on a primary amine, you then have lysine in the gamma position. If you take off 1 methylene, and 1, 2, 3, and now stick on a guanidino group, you now have arginine. And if you then have 1 methylene group and you stick on that indole ring here, right? So 2 nitrogens, we have some double bonds. We have, of course, histidine. That primary amino group of lysine, of course, has a pKa right around 10.5. pKa of that guanidino group is around 12.5, which means at neutral pH, these guys are going to be positively charged. That histidine, that imidazole group, however, has a pK closer to about 6, which means at neutral pH, and it can move around in some cases around neutral pH. This guy can go either way. It can either be positively charged or neutral, right? These guys are, of course, quite polar, again, like the acidic amino acids. These guys are almost always going to be found on surface of proteins or in contact with solvent or in situations where you need a salt bridging interaction, you want to have a hard charge interaction with something. They're super important for providing the positive side of electrostatic interactions like that. All right, what about chemistry? What do you think? Well, that primary amino group, that's actually a pretty good nucleophile, all right? It can be turned in once you pull that proton off, you deprotonate it, that the pair of electrons, lone pair of electrons on that amino group is actually a really pretty good nucleophile, right? You can get it to do all kinds of chemistry. In fact, one of the most important reactions in the biosphere, the fixation of carbon, CO2, by the enzyme rubisco, the central amino acid that does that chemistry, that activates the carboxyl, the CO2 group, is a lysine residue. And we're going to see a couple of reactions that use a similar carbon dioxide activating chemistry that's centered on lysine. Arginine, yeah, not so much. That guanidino group, in most cases, we're not going to see any examples where that's reactive. You can pretty much think about this as an inert, very positively charged amino acid. What about histidine? Anybody know some examples? Histidine absolutely can be involved in some significant chemistry. All three of these guys, arginine less so because its pK is so high. Certainly histidine and lysine can be involved in acid-base chemistries because that primary amino group and that indole ring can push protons back and forth, right? But histidine can also, you can also coax that indole ring, if you deprotonate it, the lone pair on those nitrogens, or this pair, can be coaxed into being a pretty good nucleophile. You can actually phosphorylate histidines, and you can use it in other group transfer chemistries as well, right? Okay, so that more or less brings me to the end of the amino acid bestiary that we need to talk about, right? So the amino acids on their own, it's kind of boring, right? Yeah, there's some interesting things, but they don't really do a whole lot on their own. Things don't really get interesting until you start putting these guys together into a protein. And that's the next thing we need to talk about, which is the formation and properties of the amide bond.